I once had a student jokingly say that Calc 3 is the best calc, and in a way I kind of agree with her, and the reason is because of unification. The idea is that there's like a bunch of different phenomena that can be explained using the same mathematical model. So that means that like there's a bunch of different types of problems that we can solve using the same math formula. That's kind of a good thing and a bad thing from the point of view of a student, because, you know, on one hand, this is like a really powerful tool, and on the other hand, it means that there's like a bunch of different scenarios that this applies to. So it's, you know, I mean, I think it's kind of tough to keep straight. So today I just want to give you kind of an overview of what vector calculus is, so that when you're studying, it's kind of easier to keep your ducks in a row and know where each piece that you're learning like fits into the bigger picture. Classes on vector calculus are usually broken up. So there's usually like the first little unit you do in 2 dimensions, and then the second half of it you do in 3 dimensions. So let's go over the content for objects in 2 dimensions first. The setup is always the same. You're going to have some kind of path in 2 dimensions, and the name of the path is C for curve, and then you're going to have a parameterization of the path, and you're going to call that R of t. Then there's always going to be some vector valued function, so that's going to be either a force or a velocity, and so we're going to call the x coordinate of that function m, and the y coordinate of that function n. And then there's going to be some kind of density function, delta. So delta can either be like mass density. That's usually what people mean when they say density. They mean mass density. It can also be charge density. So like an example of mass density is going to be, the units would be like kilograms per unit measure of space. So it could be kilograms per length, or, you know, kilograms per area, or kilograms for volume. So then there's 2 other kinds of density. One of them is called work density. So that's just force times distance. And then the other one is called flux density. So that setup is the same for all 2D vector calculus problems. Then the first object that you learn about is always the line integral of a scalar valued function. So this is a model for if you had like a thin wire and you wanted to find the total mass of the wire, or if you had like a wire and there was like electrical charge in the wire, variable electrical charge, so the wire was charged differently at each point. Then the line integral of those density functions, if the density was mass density, then when you added them all up, you would get the total mass. Or if it was charge density, then when you added them all up, you would get the total charge. Then there's kind of a big step. I would say, you know, as you're learning this, watch out for this topic, line integrals of vector valued functions, because there's a lot of concepts baked into this simple setup. So there's 2 kind of line integrals of vector valued functions. One that depends on the unit tangent vector, so we call that the tangential form, and it calculates work. And you'll also see, sometimes you'll see the word flow associated with that. And then the other kind of line integral of a vector valued function that you're going to do depends on the normal vector. So people will call this the normal form. So these things are models for, work. I don't really think I need to justify why work is an important thing. This is the amount of energy that it's going to take to do something. So anytime you're engineering, you're going to need to calculate the amount of energy in the system. So that is like a real standard model. And then the other one here is flux. And this is a little bit of a mysterious thing. So I just want to motivate a simple idea of what could flux possibly mean. Here's some images that I got off of Google of Niagara Falls. And according to this, NiagaraFallsFacts.com, 3,000 tons of water flow across Niagara Falls every second. So that is a lot. All right, so I've got this is like the satellite picture of it. So here's the falls. I don't know if you can see that. And the idea is that there's water flowing across the boundary. See, I just did it. Here's the other one. The thing is that sometimes we want to talk about a path, an object moving along the path, and sometimes we want to talk about it moving across the path. And in everyday language, we call both of those flowing, but in math and in physics class, in order to differentiate things, we say that we say that an object flows along the path, and we say that an object fluxes across the path. So there is water that is fluxing across the boundary here, and the total flux is the total rate at which water is passing across the boundary. So that's the other application of this. Again, the answer is apparently 3,000 tons per second. And then there is fundamental theorems. There's always two kinds of fundamental theorems. One that applies to conservative force fields. So those are force fields that have some kind of conservation law, like, for example, conservation of energy. And then there is always two kinds of non-conservative fundamental theorems. In 2 dimensions, we call the non-conservative fundamental theorems Green's theorem. It's named after a person, George Green. And both of them are relationships between what's happening on the boundary and what's happening on the inside. One of the theorems tells you how to get the total work to move a particle around the boundary, and another one tells you this example from like Niagara Falls, where it's like the total rate at which something is passing across the boundary. So let's jump up to 3D now. So in 3 dimensions, what's going to happen is so the setup is very similar. Sometimes you do still have a path, but also sometimes you have a surface. And so then your vector valued function, I named this wrong, it's not x and y and z. So then you're going to have some kind of force field in 3 dimensions, and we're going to call them m for the first coordinate and n for the second coordinate and p for the last coordinate. And then the density is the same. You can either have the mass density or the charge density, or you could have flux density or work density, just like before. And then, so line integrals of scalar functions, it's the same in 3D and 2D, except in 2D, your wire would be stuck in the XY plane, and in 3D, the wire could be moving anywhere in 3-dimensional space. So then the model is the same. This is still a line integral of density is still going to give you the total mass or the total charge of a wire. Okay, so the 3D, 2D similarities continue to be the same. When you are calculating work or flow, it's the same in 2D and 3D, except you just have an extra coordinate. But flux is different in 2D and 3D because now you're not talking about just like a satellite image, which is basically a flat thing. Now you're talking about a 3-dimensional object. These cool pictures. This first picture here is a magnet, and then they've put iron shavings on it and kind of jiggled it around so that all the iron shavings line up along the magnetic field. And, here I have another example of a camping lantern. So what camping lanterns have is they have this kind of like nylon mesh, and then gas is being pumped into that mesh, and the gas is passing across the boundary. Oh, so another example would be like when you pour coffee through a coffee filter. So any kind of like 3D scenario where you have some quantities that are passing through a surface, and you want to figure out the total rate at which, gas is coming out of what are you going to make some like giant flaming lantern? How much gas is coming out of there? How long is it going to last? This is just going on. What am I even talking about? Then just like in 2 dimensions, there's some fundamental theorems. There's one that is for conservative force fields. So that's a system that is a model for something where there's conservation of energy or conservation of angular momentum or something like that. So hopefully just take a minute right now just to go ahead and look at that formula. Hopefully when you see this, this is already starting to look like the fundamental theorem of calculus. Then there is 2 versions of the fundamental theorem for non-conservative force fields. We name them after people as well. They're named after Stokes and Gauss. So again, they are ways to calculate either the work along a boundary or the flux across a boundary. This actually shouldn't be boundary here because it's now the flux across a surface. Because in 3 dimensions, when you have, like a liquid passing through a filter, the filter would be a 2-dimensional object. So there is, that's kind of all the things that are present in vector calculus. And the beautiful thing is at the end of this, there is one big punchline, that is the culmination of all of your calculus studies, where I can take all of these fundamental theorems and you can condense them down into one very nice little statement. So you heard applications from, the motion of liquid, or, if you're trying to engineer like an electric car, you need to figure out how much work is done, to, I guess building a lantern, to, magnetism. So all of these different applications and all of these different fundamental theorems can be boiled down into one statement. So that's kind of why, I'm a believer that Calc 3 is kind of the most beautiful kind of calculus.